All right. So I'll talk about some of the work that Dr. Hugh Farm and myself have done, and we've been looking at. If I have time, I'll go to I'll go to two problems, but most likely it'll be just one. So the motivation is that what can we do with high resolution LES to understand the upper ocean structure when it is forced in different ways during the monsoon intraseasonal oscillations. One of the things that we were interested in doing is that, is to look at the simulations of a diurnal warm layer where we actually simulate on minutes time scale over a period of, I think, so we have gone up to about 7 days. So if you have the wind and you have diurnal warming, what is the response of the upper ocean? And then if you have time, I'll go into a 2D problem. So this is in the mean a 1D problem, a 2D problem when you have frontal instabilities. And this process number one, in addition to understanding this process, we're also kind of interested in finding out what do other models do. And so the idea is to use the LES as a benchmark solution in coordination with other modelers in Mesobob to evaluate this 1D mixing parameterizations and also upscaled fluxes in regional model calculations. So this is a cartoon of the LES of the diurnal warm layer. So you have this 20-meter mixed layer, and it's driven by a rather weak stress, tau of 0.062 meters squared, and then there's a halocline that is capping the mixed layer. So we do an initial spin-up to set this up, and then we add this diurnal heat flux here, as I'll show in a moment, and we will track the evolution for a period of 7 days. The domain is, so the computational grid is really small by the LES standards that we usually do, but it's an expensive calculation because we'll be doing minute resolution over 7 days. So that's what makes it expensive. And the grid resolution is super fine. So in the horizontal, it's 0.5 meters, and in the vertical, it's 0.1 to 0.2 meters, and then we stretch in the halocline. So this shows the variability of temperature and salinity, and so this shows the heat flux in here. And by the way, I'll be using negative for heat flux into the ocean. So if you look here, that the daily average temperature in the surface mixed layer, you can see it increase as time goes by. The salinity also increases the mixed layer because of the cumulative effect of entrainment, but the density actually decreases because of the warming. So the mixed layer is accumulating the heat and warming up, and so you have this little bit of entrainment going on, but that really doesn't play a big role in terms of the density. And here you see the diurnal warm layers form. So we talked about diurnal layers in the atmosphere. So this is the diurnal warm layer in the ocean. And you see this enhanced stratification during the daytime as the heat is accumulating. And as you might expect, you see the nighttime convective layer here. This is a plot of n squared is less than 0, about 10 meter deep. And the nice thing is that we're able, with this resolution and the LES model, we pick up this diurnally enhanced surface jet. And this was discussed in a recent paper in JPO. And so all the action that occurs is really over a short period when you have, so this is the shear here. So you have these diurnal shear layers that descend down to 10 to 20 meter depths. And these diurnal shear layers descend down when the surface momentum is not trapped right at the end of the warming period. And interestingly, this is an analog to the EUC study that we did in collaboration with Bill Smythe and Jim Moom. And there, what happened was that this layer, diurnal layer that came down, coupled to the subsurface equatorial undercurrent. So then you had this huge turbulence that went all the way to the core, so about 150 meters. Here, of course, you don't have the subsurface shear, so you don't see that. And of course, what you see is that these diurnal surface jet and these descending shear layers, it's always in this, in this marginal instability range. So you have a narrow range of Richardson number of 0.25. If you look at the variability of turbulence, the nighttime dissipation is very strong during the evening. So it's strong during the evening when you have this descending shear layer. It is actually stronger during the evening than in the nighttime when you have convection. And as I pointed out here, the strong dissipation is driven by the shear production associated with the diurnal warm layer and the descending shear layer. And all the action in terms of the heating of the upper ocean by the solar influx is really during this short time period of a couple of hours, in which during the late afternoon, when you have the strong turbulence that transports all the surface heat from the surface to 20 meter depth. So during the whole day, there's a short period when you get this strong warming of the ocean. So if you look at turbulent entrainment, so we are tracking the salinity here, the diurnal variability of the sea surface salinity. It increases only at nighttime, as you might expect. That's because that's the time when the mixed layer depth has penetrated down, and it's communicating. The surface is communicating with the halocline, and so that's when you get these little step-like increases in the surface salinity. The late-time entrainment rate with no diurnal heat flux in a stratified rotating ocean, you can show theoretically that it scales like so, U star squared by N0 HT. And this is, remember that this is not a thickening of the stratified layer with a wind burst. So it's already set up. And so therefore the coefficient 0.049 is an order of magnitude smaller than what you would expect if you had a wind burst going and then a mixing going down. When you have the entrainment rate of the diurnal heat flux, it's slightly larger. And this is a little bit of a boring problem, which sort of, sort of gives a stepping stone onto a more interesting problem when you have wind bursts. Then what happens? Because that's really the utility of a high resolution LES model, because it should capture the transients well by construction. So in summary of the diurnal warm layer, so what we find is that the diurnal cycle of the heat flux drives, as you might expect, a diurnal variability of the stratification, shear, Richardson number, and mixing. And here we show, when is the turbulence the maximum, when is the, as it says here, so all the downward heat fluxes in the short time period. And in future work with a bunch of modelers in the mesobob thing, we want to take a look at a little bit more complicated situation when you have the winds picking up, when you have a more interesting combination of surface fluxes, and the initial condition has a thermal inversion. So we'll see how the LES does. And equally importantly, the question is that how and why do simple 1D models work for this particular calculation. I should add that I put it in there. It's going to be a difficult calculation because with these strong winds, you have extremely intense shears at the surface, and so it'll be challenging, I think, to compute the shear and the associated turbulence. But we'll give it a shot. So the other problem is fronts and bows in the Bay of Bengal. So I talked about this in the Seattle meeting, but some of you have obviously not seen it. So I'll just go ahead and repeat this problem. And so we've already looked at, well, we all know from the series work that there are these shallow fronts, and they're all over the northern Bay of Bengal. And then from time to time, you've got these, they really sharpen, and then you got this multi-scale structure, and then you've got these gravity currents that come out, right? And we showed that a possible mechanism for that is that intrinsically, if you have an initially balanced front, even if you have an initially balanced front, but if it's strong, then it naturally goes out of equilibrium just due to the surface turbulence that develops over time if you allow nonlinearity to grow, and it can develop into bores. But really, to be honest, I mean, you need something with a very large horizontal length scale to get these correlated bores with big, long lateral scale, and that's the wind. Or it could be a mesoscale eddy, of course, yeah. So let's look at what the wind might do, and that's really what we're looking at. So we've been thinking about it from the Syrian investigators for a while, and then Drew had a nice poster, so shout out to Drew here. And so the hypothesis is that, and this is based on observations, is that if you have like this river water filament, this fresh river water filament, then you have this asymmetric mixed layer depths on the two ends. And so we have done a process study to look at that. And I don't think I have much time left. I have probably no time left. So do I have like a minute?
Sure.
Okay.
Yeah.
All right. So this is the evolution of salinity. And so overall, the entire filament is advected laterally by the Ekman transport. So wind is growing into the board here. On the right, you have got the Ekman transport going on. And then you have the upfront side here, and then you have the downfront side here. And you can see within 24 hours, you've got this asymmetric evolution. So you've got this much thicker mixed layer because of convective mixing, and you've got this thinner mixed layer, and as I'll show, that actually steepens out and goes off into a gravity current because the Ekman transport reinforces the ageostrophic secondary circulation associated with the front. And this just shows a little bit more the lateral velocity in here. And so on the upfront side, you have a strong ageostrophic secondary circulation. You've got this, so this is V, lateral velocity. And so you have this positive velocity, so the fresh water is running to the right as a gravity current, and then you have a subducting countercurrent that goes down and actually collides with this guy that's going in. So you've got this interesting bulge right at the, where these two collide. And this shows a three-dimensional perspective of the turbulence structure in here. So you've got these, if you look at the downfront side, which you remember has a destabilizing Ekman buoyancy flux, you get these convective plumes with this lateral spacing of 300 meter. So this is very fine scale turbulence, but overlaid there is this natural instability mode that seems to occur. On the upfront side, the story is quite different. And here what you have is that you can see a very thin mixed layer that forms, and you get these localized patches of turbulence, no convective plumes. if we are doing a further analysis, these are basically mixed KH type billows that develop in this gravity current that's running off. And I should really stop here. So this is the freshwater element summary.
Thank you, Sutanu. I'll take one question before we break for lunch. Thank everybody.
Great questions on the time scale. For your gravity currents, I haven't really said much about the time scale of
A few hours.
hours.
Few hours. Because it's a very, few hours. And the gravity current is really set up on the upfront side. So in the downfront side, actually there's frontal assist. Because, yeah.
And that's hours.
In hours, yeah. Yeah.
Right. Any others? I'd like to thank all the speakers for this session. You did a wonderful job keeping to the time, and we hope we'll maintain this throughout the next two sessions. Thank you.